Welcome back. This is Mr. Wakefield. We are currently in section 7.1, and this is now part 2 of section 7.1. We've already done the front side of the worksheet. As we turn the worksheet over to the back, we're going to look more at these problems with the sigma letter and the series where you add up a bunch of terms. So let's go ahead and flip that worksheet or that page over, and we'll go ahead and take a look at those problems on the back. As we move on to the next set of problems here, you'll see in number 7 that the bottom number is 3 this time. Usually it's going to be 1 more often than not, but not always. Okay, so what does it mean if the bottom number is 3 and the top number is 6? It means that, in fact, let me pull it off to the side over here. It is going to be, it's trying to tell you to do A3, A4, A5, and A6. That's what it's trying to tell you to do. Okay, not A1 and A2. All right, so what is those 4 terms going to be equal to from 3 up to 6? Okay, let's take a look. So, 2 times 3 squared plus 1. 2 times 4 squared plus 1. Okay, you're plugging in 3, 4, 5, and 6 into that bracket that's right next to the sigma letter. By the way, whenever you have a bracket next to the sigma letter, the entire bracket is your sigma letter, and then, the entire bracket, when there's a bracket next to the sigma letter, the entire bracket is the thing you plug into. Now, if you have an exponent like we did in problem number 6 just a moment ago, all right, if you have a bracket there, then that would also be included as well. Okay, but if you had, let's say you had a plus outside of the bracket here and you were adding something else, we'll see that in the next few problems here coming up. We'll see that in some of the problems that we see coming up here, at least eventually in the problem. Not in the original problem, but you'll see it in the steps of the problem. If you see a plus after you see like a term or a bracket, even an exponent, okay, that would then separate the rest of the problem from the current sigma letter that you're looking at. So just want to make you aware of what you plug into. So if there had been like a plus after this, all right, whatever goes after that plus would not be part of the thing that you plug into this particular sigma letter. Okay, again, we'll get into that coming up in some of these future problems here on this worksheet. Anyway, so, but yeah, if you see a bracket, I just want to make it clear, you're not just plugging into 2i squared. You're plugging into the entire bracket. And if there's an exponent like there was in number 6, that counts also as part of the thing that you're plugging into as well. Doesn't mean you plug into the exponent, but that's part of the entire math expression that you're plugging the 3, 4, 5, and 6 into. Or in the case of the last problem, 1, 2, 3, 4, and 5. All right. So we plug in 3, 4, 5, and 6, like I said. If we do order of operations on this, exponents come first. So we get 2 times 9 plus 1. 2 times 9 plus 1 is 18 plus 1, which is 19. Next one is going to be what here? It's going to be exponents first, so we get 2 times 16. We multiply that, it's 32. 32 plus 1 is 33, and then we do that same thing with the other two here. 5 squared is 25, times 2 is 50. 50 plus 1 is 51. And finally, 6 squared is 36. 36 times 2 is 72. Plus 1 is 73. So, again, this is not like the first 2 problems, is it? Because we got the sigma letter this time. It's not like the first 2 problems, problems 1 and 2 on the front, where you just figure out all the different terms and you're done. Okay? No, the sigma letter tells you to add them together now. So we get 19 plus 33 plus 51 plus 73, and you just have to add those up. Okay? Certainly you can use your calculator to help you here. 19 plus 33 is 52. Plus 51 is 103. 103 plus 73 is 176. And that is number 7. Okay. Now, in these next few here, the next couple ones in particular, notice that the numbers on top are pretty darn big. Okay, it looks like they're telling us to plug in a whole bunch of stuff here. If you go from 1 to 20 and you plug in every number from 1 to 20, isn't that 20 numbers you plug in? And if I got to plug in every number from 1 to 50, isn't that 50 numbers I got to plug in? Oh my gosh, that's terrible, right? Well, normally it would be terrible. But there's a shortcut that I need to show you. And that's why I have those problems on this worksheet. So you learn those shortcuts. Okay, let's learn about that. In the front side of your worksheet right now, there's these things called rules for sigma notation. Please, 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 you guys, be careful to not invent your own rules. Okay, all right. Let's go over these carefully and stick just to these rules here. All right. This says here that if you have a constant number, the C is a constant. Okay, if you have a constant number being multiplied by a term, in this case we call it AK. All right. The reason why it says AK is because the K is the number that is the variable in the problem that you plug into instead of I. Sometimes they use the letter K, sometimes they use the letter J, okay? By the way, when they use the letter I forgot to mention this. When they use the letter I want to make it clear, that's not the same I that we saw earlier in the semester for imaginary numbers. When you see I with a sigma letter, you guys, or just talking about sequences in general, all right, figuring out terms of a sequence, series with sigmas and all that, okay, I in that case means that it's just a variable. Earlier in the semester when we were talking about imaginary numbers, I is the square root of -1, okay? It was actually a constant number equal to the square root of -1. But here, it's just a variable. So it just depends on whether or not you're talking about sequences or series, okay? So here, it's just a variable. Anyway, so when it's written like that, and we'll see this type of example coming up here, then you can factor out the constant. It has to be a constant, and it has to be multiplied by the rest of the thing that's next to the sigma letter that you plug into. It has to, otherwise it's not going to work. Okay, I'll show you an example of that coming up here. But what does apply to this current problem, number 8 right here, is this next rule. This next rule says that if the entire thing next to your sigma letter, if that entire thing is just a constant, which we have here, it's just 5, right? There's no variable here, is there? It's just a 5. Okay, if that's the case, then the answer is just going to be the constant times this number on top, assuming that this number down here is 1. If this number down here is not 1, then you can't use this rule. Again, we got to be careful that we know exactly what the rule says. You can't divert from that. You can't make up your own rule and say, oh, hey, I'll use this rule even when the number down here is 3 or 4 at the bottom here. No, you can't do that. Okay? If this number is 1, though, and that is a constant thing right there, there's no variable here next to the sigma letter, then you can use this. What is it saying? It's saying that the top number, if you multiply that, that's the n. Okay, there's the 20 right there. If the 20 is here and this is a 5, which is a constant, there's no variable there, then the answer is just simply 5 times 20. Okay. Now, I'll write down that answer in just a minute. I want to show you why that's the answer, though. It's always nice to see why these formulas work sometimes if we have time to talk about that. The reason why that's true, and you don't need to write down, I'm going to show you the long way to do it. You don't have to do this. You can just say 5 times 20. Please don't misunderstand me. Okay. But if I plug a number into a constant, you can't plug it in, right? Because there's no variable to plug into. We didn't see this a whole lot earlier in the semester, but sometimes you got this thing called a constant function. Okay, this is very similar to what we have here. Since there's no variable here, no matter what number you try to plug into it, the answer is always going to be 5. If I say, hey, what's f of 1 equal to? It's going to be equal to 5. If I say, hey, what's f of 2 going to be equal to? It's still equal to 5. No matter what you plug in, it's going to be equal to 5. Sorry, I meant to say 5 right there. There it is. Okay, no matter what you plug in, it's equal to 5 because 5 is constant. There's no variable there. Constant means it never changes, right? That's always going to be that same answer. It's the same thing here. If I try to plug in 1, if I try to plug in 2, if I try to plug in 3, if I try to plug in all the numbers between 1 and 20, the answers are always going to be 5, 5, 5, 20 times, right? Because you got to plug in 20 things, all right? I'll just say dot, dot, dot. I don't want to write 25s here, so I'm just going to say dot, 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 and then 5 right there. And I'll just say right here in a note here that this is 20 5s that I have here. Again, you don't have to write out this part. This is the long way. Okay? So if you plug in 20 numbers and they're all equal to 5 because the thing you're plugging into is constant with no variable, then that's the same thing as adding up 5 20 times. And what happens? What is the when you learn multiplication when you were a little kid for the very first time? How did they teach you multiplication? Didn't they tell you that multiplication was just the same thing as adding up the same number a certain number of times? Okay, 20 times 5 is the same thing as adding up 5 20 times, isn't it? Just like 3 times 7 is the same thing as adding up 3 7 times. Or adding up 7 3 times. It's going to be the same answer either way. Okay, so if you add up 5 20 times, all right, that's the same thing as 5 being multiplied by 20. And so that's all you need to write. I just wanted you to see why it's equal to 5 times 20. I wanted you to see why this formula down here actually works. So the final answer then would be 100, wouldn't it? 5 times 20 is 100. Okay, now, moving on. Number 9. That's where this first formula comes into play here. Okay. We actually have a formula, okay, for I to the third right here. Okay. In fact, I have a formula for both I and I to the third down here that we're going to use in this set of problems here, because you can see I here and the I to the third here, so we're going to see that again. These two right here, these two formulas, you don't need to memorize these for the exam. I will give these to you if you get a problem where you need it. Okay, I will give these to you. Again, please understand, just like the formulas on the front of the worksheet, okay, this says 1 at the bottom. This only works if it's 1 on the bottom. 1 on the bottom, okay? I will give these to you if you need them, though. All the other formulas, though, you need to memorize, okay, including these 4 on the front where it says rules, okay? But these two, all right, I'm not so much concerned that you know these as much as you know how to use them. And so that's why I'm not going to make you memorize these. I just want you to know how to use them as part of a bigger problem that you're doing. Okay, so notice that we know what I to the third would be equal to if that was the term. But that doesn't mean that I know what 2 times I to the third is. But there's good news. As I just mentioned, when you have a constant, which 2 is, when you have a constant times the rest of the term there, in this case, 2 would be the constant, and I to the third would be the rest of the term. Here would be the AK part. If you have a constant times the rest of the term there, okay, you can move the 2 out to the front of the sigma to be multiplied by it. And that's good news because now the sigma has what to the right of it? Okay, the 2 is now gone. It's now to the left instead of to the right. So the only thing that is to the right of the sigma letter is I to the third, not 2I to the third. Okay, I want to make it clear, you guys, this is only if it's multiplication. If this had said 2 plus I to the third, you can't do that. We'll talk about how to do addition, though, in just a minute, though. But if it's 2 plus I to the third, you can't do it. If it's 2 minus I to the third, you can't do it. If it's 2 times I to the third, if it's times, and the 2 is a constant, you can pull it out. If this had said I squared times I to the third, you can't pull out the I squared because that's got a variable in it. You can't factor something out of a sigma letter to the front of it if it's got a variable in it. Again, it's got to be a constant. Okay, but now that I've done that, All right, now that I've exercised rule number 1, that's good news that I'm able to do that, because now that I just have I cubed there, okay, I can then use this rule right here. All right, I can then use this rule, bring it up, and it says what? It says, and don't forget the 2 there, the 2 still there. 2 times what? Well, this thing right here is going to be what? It is going to be equal to this. Okay, so that means that, again, you have a 1 on the bottom and you have a 1 on the bottom here, so that it matches. Okay, so that means you're allowed to do it because it matches up. So that means that whatever this number is, 50, you then plug in the 50 here and here. So like if that had been a 10 on the top of the sigma, then you'd plug in 10 squared and then 10 plus 1 squared. That's how it works. But because it's 50 on top, you're going to have 50 squared and 50 plus 1 squared. Let's write that down. 50 squared and 50 plus 1 squared divided by 4. And again, the 2 is being multiplied by that because it says the 2 is being multiplied by whatever the sigma is equal to. Okay? Now, so what is all this stuff equal to then? Okay? Well, it says to evaluate the problem. That's what it said in the front side in the directions. Evaluate each series. All right? If they say to evaluate something, that means to figure out what it's equal to. If there's no variables in something that you're evaluating, okay, then you do order of operations. Okay? When you have a fraction and you're doing a big fraction with operations inside of it, like exponents and multiplication and addition and all that, one thing that you can do, all right, is you can figure out what the fraction is equal to first, and then do order of operations based on that answer that you get. But they do that first, though, especially in these series problems, because you're going to get some big fractions. Figure out what the fraction is equal to first before you multiply it by 2 and do the rest of the problem, in other words. Okay? So let's figure out the fraction first. Now, what does it mean to figure out what a fraction is equal to? As I mentioned a few minutes ago, and as I've mentioned many times this semester, it means to figure out what the top and bottom are equal to, and then put it in lowest terms after that. Again, if there's no variables. Okay. Because if there's no variables, nothing's going to stop you from figuring out the top and bottom. So this is going to be what your calculator, again, will help you out here. This is going to be 2,500. Okay, times 50 squared is 2,500. And then what is 51 squared? 51 squared, I'm just going to pull this, figure out what that is on my calculator here. Actually, you know what? I got a little bit ahead of myself here. Not that it's a big deal as long as you're careful. But this is actually, I'm going to be a little bit more careful, though. I need to do my parentheses before my exponents, right? Okay. So, after you do your parentheses, you then do your exponents, and the exponents are going to be equal to 2,500 for the 50 squared. And then it's going to be 2601. Again, your calculator will tell you that. 2601 for the 51 squared. Then we figure out what those two things equal, and it's equal to a big number here, 6,502,500. This is why you would not want to go without using the shortcut here. Okay, you would not want to be plugging in the numbers from 1 to 50 times. Okay, 1, 2, 3, 4, 5, all the way up to 50. That would take absolutely forever to do that. Okay, don't even think about doing that. Make sure you know how to do the shortcut with this formula and being able to factor out the 2, because you can't use this formula down here, you guys, unless it's I to the third, right? You got to get that 2 out of there and put it in the front. Now that I know what the top and bottom are equal to, and I apologize, you guys, I'm getting a little bit careless here. I forgot to bring the 2 along here. Let me just bring it back in here again. The 2 is still in front of that. Okay. There we go. 2 times that fraction. So again, we're still trying to figure out what the fraction is equal to. All right, that means that we put this in lowest terms after I figure out what the top and bottom are equal to. I now know what the top and bottom are equal to. When you put something in lowest terms, though, you guys, always try to divide it first, straight out, top divided by bottom, okay? Because a lot of times, especially in these problems, it is going to divide evenly. So no use trying to, like, you know, do all the other stuff you normally do to put things in lowest terms, you know, like dividing the top and bottom by the same number and all that. Try to divide it straight first by 4, and then if it divides evenly, then that is actually the lowest terms number. If a fraction divides evenly, top divided by bottom, then the lowest terms that you need to do is going to be simply equal to that answer. Because it's the same thing as 1625, 625. It's the same thing as having that number over 1 when you put it in lowest terms. But you know that when you put something over 1, you don't need to write the 1 there, right? Okay, so if I put this fraction in lowest terms by just doing it in the normal way, dividing the top and the bottom by the same number, it's just going to be equal to this number right here divided by 1. Okay, so might as well just put it in the calculator if it ends up being a whole number that divides evenly. Okay, if it's a decimal, don't do that, okay? Unless it's one of those decimals that doesn't cover your whole screen, then it would be okay. The important thing is we want an exact answer here again. But putting in the lowest terms, try to actually divide it, though. That's my point. Try to divide it, okay, and see if it divides evenly. Then you get a nice, simple answer there. You don't have to do any of that other normal lowest term stuff. What happens when you multiply this by 2, which is what you do after you figure out what the fraction is equal to? You then do order of operations on the answer. We got the answer times 2 here. And that's going to be what? That's going to be, if I put that in my calculator, times 2. Again, a very big number here. 3,251,250. Okay. And that's number 9. Okay, moving on to number 10 now. Again, when you have a parenthesis next to the sigma letter, it does apply to that entire parenthesis, not just to the 3i. Okay, so the numbers that you're going to plug in are going to get plugged into this entire parenthesis wherever you see the variable. Now, since it's a 1 on the bottom and a 6 on the top, that means that we're going to plug in every number from 1 to 6, correct? 1, 2, 3, 4, 5, 6. That's what you would normally do, okay? And you could do that if you wanted to. But again, these rules that we have right here are going to allow us a little bit of a shortcut here. All right. And so let's talk about that. Since this is plus, since you have two things being added together here, 3i plus 2i to the third, okay, that's the same thing as this right here. Again, if you have a parenthesis next to the sigma and it's got two things being added, two terms being added together, same thing if they were being subtracted, then you can do this thing right here where you split it apart. And that's going to be very beneficial to us, as I'll show you here in a minute. Okay, if you're not seeing that yet, don't worry. I'll show you why it's a good idea to split them apart like this. Okay, but you could do that. All right. Again, this only works for addition and subtraction. If it's AK times BK or if it's AK divided by BK, you can't do it. There's no formula for that. Again, do not invent your own formula. Stick with I'm sorry, don't invent your own rules. Okay, stick with the rules that we have here. All right, use only those. Let me do that here, and then you'll start to see why that can be done, or why that's important to do it. But notice again, it has to be a 1 on the bottom in order to do that. However, this problem is a 1 on the bottom, so that's why I'm doing it. Okay, notice up here in number 7, why did I not do a similar thing here? I got a term plus a term inside the bracket, right? Why did I not do the same thing in number 7 as I just talked about here for number 10? Okay. In fact, let me write it out so you can see the two problems right next to each other here. Why did I not do that in number 7 where I split it apart like this? The reason why is because you'll see up there on number 7 that it has a 1 on the bottom. I'm sorry, on this one it has a 1 on the bottom. This one it has a 3 on the bottom. That's what it all comes down to. Okay. If you do not have a 1 on the bottom, then none of these rules work. All of these rules have a 1 on the bottom. All the sigma letters do, right? All of them do. And so because that out of 3, I had to do this problem the old-fashioned way, which is just to plug in the numbers one at a time. There's no shortcuts, okay? Just when you have a 1 on the bottom, do these rules work? But since number 10 has a 1 on the bottom, I'm going to take advantage of these rules, okay, in order to make the problem shorter. Let's keep going. All right, now, remember you guys, I've got these formulas down here, right? If I can make the thing next to my sigma letter on the right-hand side of it, if I can make it equal to I and I to the third, I can then use these. How can I get rid of the 3 and the 2 from the right-hand side of each sigma letter right here so that I can just have I here without the 3 and just have I to the third right here without the 2? I can use rule number 1 right here, right? Since 3 and 2 are constant numbers, and they are being multiplied by the rest of the term that's next to each sigma letter right there, you can then move them out to the front. Okay, let's write that down. There we go. So the 3 can be moved to the front. And then the 2 can be moved to the front also. Okay? Like that. Okay. So then, now that I have I and I to the third next to each sigma letter right there, that means I can now take this right here and I can use this one for that because this says I next to the sigma letter and it's got a 1 on the bottom like this one does. We're good. And then this one right here has I to the third, but I to the third applies to this one right here, so I can use this one. So I can use this formula for this one, and I can use this formula over here for that one. I and I to the third. You might be wondering, is there a formula for I squared? Yeah, there is actually. We just don't need it on this worksheet. But there is one, okay, in case you were curious. So, what does this become? Well, just like in the last problem, you use what it's equal to here with the n in it to figure that out. Okay, I was actually looking at the wrong. I meant to look at this one here. So for I, it's going to be n plus 1 over 2. What is the n? The n is the thing on top. So since the thing on top is 6, that's going to be 6 plus 1, 2. Let's write that down. Like that. Okay. So 3 times what this sigma letter is equal to, which is this fraction, plus, let me bring the plus over, plus 2, bring that over, times whatever this sigma letter is equal to. And that sigma letter is equal to this one right here. Okay? N squared, n plus 1 squared over 4. We used that in the last problem, right? Okay? So since the 6 is on top, we now have what? We have 6 squared, 6 plus 1 squared over 4. Let's write that down. And now we need to evaluate this. There's no more variables left. Okay, we've plugged in everything. Okay, no more variables. We just need to figure out what it's all equal to when there's no variables and you're just trying to figure out what it's all equal to, you do order of operations. But as I mentioned in the last problem, if you have order of operations and you have fractions, okay, figure out what the fraction is equal to by, and that's what you do first. You first figure out what the fraction is equal to by figuring out what the top and bottom are equal to, and then put the fraction in lowest terms, if that's not done already. And that's clearly not done with these fractions. We got some calculations to do. Okay, but once you're done figuring out what the fraction is equal to, with the lowest terms and all that, then you do order of operations on those answers that you get. Let's see what we get here first. This would be 6 times 7. I'll just put a 7 right here so we don't have to keep on rewriting it. 6 times 7, which is 42 over 2. And then I'll figure out the lowest terms for that in a moment. Plus what? Plus 2 times, and then this one would be 6 squared times 7 squared, wouldn't it? 6 squared times 7 squared is what? That is 36 times 49. 36 times 49 over 4. Okay. What is 42 over 2 if you put that in lowest terms? It is equal to 21. Again, that's another problem where if you just do 42 divided by 2, as long as it's a whole number and it's not a decimal or fraction, okay, then that's better than trying to put it in lowest terms the normal way. Okay, it's just a normal whole number. Great. Okay, so just put 21 there. And then 2 times what? Well, 36 times 49 is equal to, let me put that in my calculator. 36 times 49 is 1764. And then 1764 divided by 4. Put that in lowest terms. Again, try to divide it evenly to see if it's a nice whole number, though, first. 1764 divided by 4. Let me put that in here. And yes, it is a nice whole number. And so I'll go ahead and use that. What do we get? We got 441. So now I do order of operations on the answers that I get from the fractions. All right, in other words, I have 3 times 21 and 2 times 441. So I just do multiplication and addition and I'll be done. 3 times 21 is 63. 441 times 2, put that in your calculator, that will be equal to 882. And then finally we add the final answer after all of that is equal to 945. Okay. So, by utilizing these rules and by utilizing these formulas, you can then figure out what some of these bigger polynomials are equal to. As long as there's a 1 on the bottom, you can do that. You can do the thing where you split it apart until you finally have the I and the I cubed, okay, in there. And if I ever have I squared in there, I would give you the formula for I squared as well. Like I said, I don't have it on the sheet here today because it's not on, the I squared didn't ever come up, okay, except for in number 7. But like I said before, you can't use this strategy of splitting the thing apart in problem number 7 up here because there's a 3 on the bottom. So that was different. Okay. One other note here, in that problem on the front here, number 6, why did I not split up the I and the 1 into 2 separate sigma letters? I've got a plus right there. It's because of the exponent. Okay. Notice here in the formula that it says 2 things being added together in the parenthesis. It does not allow for an exponent outside here, though. It's just 2 things being added together in the parenthesis. That's when you're allowed to split those 2 things up into 2 separate sigma letters. Okay, but not when the -1 is there or any other exponent on the outside of the parenthesis. Okay, an exponent on the outside of the parenthesis is not allowed here. Okay. So last thing we're going to talk about here in this section is we're going to kind of go backwards now, all right? This is what, these 2 things right here are what your answers would look like, at least initially, if you plugged in a bunch of numbers into a sigma notation type of problem. In other words, a series, okay? Because you see how you got all those additions there? Okay, and that's what a series is. It's when you plug in, unless you do these shortcuts I showed you, it's when you plug in a bunch of numbers, all right, like we did up here. You plug in a bunch of numbers, all right, and then you add up the results, all right. We saw that on number 6 as well on the front. Plug in a bunch of numbers, you add up the results. Okay, that's what this thing looks like here. Even this one looks like that here as well, because remember, subtraction is the same thing as addition, except for you're adding a negative. So this would be like 1 plus -1/4, plus 1/9, plus -1/16, all right? And then I'll talk about what the ... means here eventually as well. But this is supposed to be the answer that you would get when you plug a bunch of numbers into a series with a sigma notation. So what they want you to do now is they want you to figure out what sigma notation that this answer came from. So it's like you're going backwards now. You're saying, hey, this is the answer. Now what's the question? What was the question that this answer came from? All right, and it says use summation notation. What does that mean? It means the sigma letter. It means four things here. It means a sigma letter. It means put the I equal to, and then you put the number underneath it that you're going to start with. It also means to put the number up above it that you're going to end with, and then you also have you have to have the formula that you plug all those numbers into. Four things, just like on all our sigma letters, you guys. All of our sigma letters have four things: the sigma letter itself, the number underneath, the number up above, and then the thing you plug into. Those four things. That's what they want you to do in these two problems. Okay, so let's write down our sigma letter. Okay, now notice that when you look at this answer, notice that it's a fraction, of course. So since all of the answers that you get are fractions, it would make sense that the thing that you plug into is going to be a fraction. Okay, and so let's split this up into two parts. Let's look at the numerators. And let's look at the denominators. Notice that the numerators don't change. 5, 5, 5, 5, 5, right? Okay. And by the way, there's a bunch of missing terms here, but we'll talk about that as well. That's why the dot, dot, dot is there. Okay. There's some missing terms in between 5/8 and 5/16. Okay. We'll deal with that. Okay. But they follow a pattern here. You can probably tell that 5/6, 5/7, 5/8. You could probably tell that the next one's 5/9, and then 5/10, and then 5/11, and it's going to keep on going until it gets to 5/16, right? That's why they say 5/16 on the end. They're telling you that that's where it ends. Okay. Remember, this is not a full-blown sequence where the dot, dot, dot goes on forever, all right? This is part of a sequence where you just add the sum of the terms of the sequence together. That's what a series is usually. Okay, and we'll see an exception to that later, but usually with a series, you start somewhere and you end somewhere. Okay, you start with, for example, you start with 1 and you end with 6. All right, so the dot, dot, dot is just telling you what's in the middle there, but it does definitely end somewhere. It ends at 5/16. Okay, so anyway, we know that there's some missing things in there, but going back to the numerator and denominator again, since the numerator is going to be constant, that would make sense that the thing you plug into is also going to have a constant numerator, 5. Okay. If I'm plugging a bunch of numbers into this fraction, in order to make this 5, 5, 5, 5, 5 all the way across the top, it would make sense that you would want the thing you plug into to be a 5. If you put a variable on the top, it's not going to stay as 5, is it? It's going to change because that's what variables do. As you plug in different numbers, it's going to cause the answer to change on the top. So if the numerator is constant, make the numerator constant here. And then how about the bottom here? The bottom does change. Since if you're looking at something that does change, in this case the denominator changes, you're going to want to have a variable there. So since the denominator changes, I'm going to want to have a variable down here. Now that doesn't mean I just stick a variable there and then stop. I don't want to just say I and that's it. This is not my answer. I'm just saying, what if I did this, okay? What if I just stuck an I there? Okay, well, it depends on how you set it up. There's multiple ways to do this problem. But normally, we usually start it with 1, don't we? I'm not saying you have to do that, okay? We're not going to be doing any of this shortcut stuff here, so it doesn't have to be a 1 on the bottom. But let's just say that I did. Okay, what would this have to be so that when I plug in 1, the first answer would be 5/6? Wouldn't it have to be 1 plus 5? When I plug in 1 right here, wouldn't I have to add 5 to it in order to make it equal to 5/6? 5 over 1 plus 5? And then if I plug in, let's see if that actually works now. The next number you plug in would be 2, right? Because if you start with 1, the next one's going to be 2, and then the next one's going to be 3. Okay. If I plug in 2 now, then I'm going to get 5 over 2 plus 5. Isn't that equal to 5/7? So it's working, isn't it? Okay. And if I plug in the next one, 3, I'm going to get 5 over 3 plus 5, 5/8. So it's working. All right. So it's working, but let's make sure that we end now. We still need one more thing. We need the number on the top. We have the number on the bottom. We have the thing that we're going to plug into. We've got our sigma letter written down. The only other thing we need is the number on the top. What would I need to plug in order to get 5/16? wouldn't this have to be 11 right here? Because then you'd have 11 plus 5 equal to 16 on the bottom. So doesn't that prove that this has to be an 11 right there? And I did it. I've got all 4 parts that I need. Okay, so again, if you've got a fraction that has constants in one place and changing numbers in the other place, keep the part that's constant as a constant when you actually set up the formula. But then the part that changes, in this case the denominator, that's where you're going to want your variable to be. Okay, but adjust it by putting in this case you're going to put the plus 5 there. Adjust it so that when you plug in the numbers and check your answer, it's actually working. It's actually giving you the correct things. 5, 6, 5, 7, 5, 8, and so on. Let's try that one more time now. Put your sigma letter down. We've got fractions again, right, except for the first one. But you can make the 1 into a fraction as well so that everything's a fraction, right? And once again, it's just like the last problem, you guys. The numerator is constant, isn't it? 1, 1, 1, 1, 1, 1, 1 all the way across. So I can, now you might be wondering, well, what about the negative signs? I'll get into that in a minute here. In fact, I'm going to make a little bit of space for that. I need to write something down right here in order to account for those minus signs. Okay, so I'll get into that. Whenever your signs alternate from positive to negative to positive to negative, we're going to do something that we saw on the front side of the worksheet. Okay, again, I'll get to that in a moment, but right now let's focus on the fraction. The fraction is always a 1 on the top if you don't include the negatives, so I'm going to put the 1 there, all right, to account for that, just like I put the 5 on top over here. Now, how about the bottom? Do you see a pattern there on the bottom? 1, 4, 9, 16, 25. The next one, I kind of gave away the answer there. The next one would be 1 over 25, wouldn't it? And the next one would be 1 over 36. But why is that true? Why is it 1/25 and 1/36? It's because this is what? 1 squared, 2 squared, 3 squared, 4 squared. Isn't that the pattern? And so if I start out at I equal to 1 again, which is optional, but I would recommend you do that, okay? If you start out at I equal to 1 again, wouldn't you want to square whatever you plug in? If I plug in 1, I get 1 squared in the first fraction. If the next number I plug in is 2, which it would be, if the next number I plug in is 2, I would get 2 squared on the bottom. It matches up. The next number that I plug in is 3, so that would give me 1 over 3 squared. Again, it matches up with what I have in the next fraction. Everything's working. But I still need to account for the fact that I have a what? The fact that it's positive, negative, all the way down. Okay? Well, on the front side of your worksheet, what did we find out? We found out in this problem that when you have alternating signs, all right, what caused that? It's this thing right here, the -1 n minus 1 thing. That's what caused it. Okay? It doesn't mean that your exponent always has to be n minus 1. All right, or I minus 1 in this case, since I is going to be our variable now. You'll see here on these series problems, by the way, with series, usually they use the letter I instead of n, just to clear that up. Okay, when we talk about just sequences without series, usually they use the letter n, usually. But with series, they usually use the letter I, or sometimes K, like you see up here. All right, you'll even see the letter J in a future section with series, but with sequences, they usually use the letter N. But the point is that that's the variable you plug into. Anyway, it doesn't have to be n minus 1. It could be n or n plus 1, usually one of those 3 things, but whatever works is what's important. So let's try it. You could do n minus 1, you could do n plus 1, you could do any of those things as long as it works. Let's just try out n and see if it works. So I'm going to say -1 to the n. Put it in front of the fraction here because it's going to be, just like in this problem here, it's going to be multiplied by the fraction. Just like I multiplied the -1 n minus 1 times the bracket, I now want this thing right here, the -1 to the n, I want that to be multiplied by the fraction here so that it'll alternate the signs. Okay. Does it work? Well, if I plug in -1, if I plug in 1 here, I get -1 to the first. oh, that's not going to work here because -1 of the first is negative, but this is positive. Okay, this is positive right here. So what you do when that happens, when n doesn't work, you can either do n plus 1 or n minus 1. N plus 1 and n minus 1 actually will give you the same answer when you're taking -1 to that power. It will every single time. So you could choose either one. I'll just do n plus 1. But look at what happens when I do that. If I plug in 1, I get -1 squared, don't I? 1 plus 1 is 2, so -1 squared. Isn't -1 squared equal to +1? And +1 times the fraction is going to give you the positive fraction here. But then when I plug in the next number 2, I get -1 to the third. -1 to the third, though, is -1, which is then going to make this equal to -1/4 when you multiply -1 times the fraction. So that's why n plus 1 works instead of n. Okay? If it had been, if this had been negative first and then positive second, then you'd want to do the n here, okay, instead of n plus 1. Again, whatever works, you guys, whether it's n plus 1, what's important is that you're getting, what's important is that this whole sigma statement that you're making here is producing these fractions with the correct signs. So that leaves us just with just one last thing we got to do, okay? This is the last fraction, isn't it? Okay. What must be the last number you plug in then? Well, 400, you guys, is the same thing as 20 squared. 20 times 20 is 400. I know that because the square root of 400 is 20. You can put that in your calculator, square root of 400. So that proves that the number on top here must be 20, so that the last answer you get would have 20 squared on the bottom here. I squared would then give you 20 squared equal to 400. Okay, so we did it. All right, so when you got the alternating signs, do that -1 thing. And it'll either be n or n plus 1 or n minus 1 as the exponent. All right, whatever works is what's important, like I said. Okay, so that concludes section 7.1. We'll be talking plenty more about sequences here in the next few sections. We'll learn how to use it for some other, we'll have some other applications of sequences and series as well. Some interesting ones, in my opinion, in fact. But first things first, make sure you understand this section and let me know if you have any questions. You take care and have a good day.